Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
Hello friends. In this video, we will study the measurement of self-inductance using the Hayes bridge. This bridge is a modification of the Maxwell inductance capacitance bridge, and it measures the self-inductance in terms of the variable standard capacitor. So let us start with our topic. So this Hayes bridge, it is named after the scientist who invented it, and it is used for the measurement of self-inductance. As I have said, that it is a modification of the Maxwell inductance capacitance bridge, because in the Maxwell inductance bridge we are having the capacitor which is connected in series with a resistance, whereas in the Hayes bridge the resistance and the capacitor, they are connected in a parallel combination. So that is the only difference between the Hayes bridge and the Maxwell inductance capacitance bridge. Both the bridges, they measures the self inductance in terms of a capacitor. Okay. So in Maxwell's bridge, we are having a parallel combination of resistance and capacitance. Whereas in Hayes bridge, we are having the series combination. Okay. So Hayes bridge, it is a type of alternating current bridge. So in the bridge network, we know that we are having 4 arms, and in the 4 arms we have the 4 impedances. Out of the 4 impedances, 1 impedance is unknown and the remaining 3 impedances are known to us. The impedances are a combination of the resistance, inductance and the capacitance. Okay, so we can have any of the combination like series combination or parallel combination in the circuit, and we are going to measure the value of the unknown impedance in terms of the known impedances to us. So Hayes bridge, it will also have 4 arms, and in the 4 arms we will have the 4 impedances, that is Z1, Z2, Z3 and Z4. These are the 4 impedances. Out of these impedances, Z1 is unknown impedance, and the remaining 3, Z2, Z3, Z4, these are the known impedances. Means the value of these impedances is known to us. We already know their value, and Z1 we want to measure. Now we know that the balance equation for a general alternating current bridge is Z1 Z4 is equals to Z2 Z3. This is the balance equation for an alternating current bridge. So Hayes bridge, in that we will equate the value of, or we will first get the value of all the 4 impedances, and then we are going to put the value of these impedances in this balance equation, and through this balance equation we will get the value of Z1 in terms of Z2, Z3 and Z4. So let us first see the circuit diagram or the circuit configuration of this Hayes bridge. This is the circuit diagram for the Hayes bridge. In this bridge, we are having four arms AB, BC, CD and DA. In the arm AB, we are having a resistance in series with the inductance. This resistance and inductance value we want to measure. Okay. Then R3 and R4, these are the two known non-inductive resistances. R4 is also a known non-inductive resistance and C4 is a variable standard capacitor. Okay. So here we will measure the value of this L1 in terms of this capacitor C4. D is the detector which is used to obtain the balance condition, and this is an AC voltage source which is providing the power supply to the bridge network. Now the total voltage provided by this is E, capital E, and this E is divided on each of these branches. So E will be equals to E1 plus E3 and also E2 plus E4. E1 is the voltage drop across the AB arm. E3 is the voltage drop across BC arm. E2 is the voltage drop across AD arm, and E4 is the voltage drop across CD arm. I1 is the current. I1, I2, I3 and I4 are the currents flowing in the respective arms. So this is the complete bridge network. Now we are going to write the configurations of all these arms A, B, B, C, C, D and DA. Arm AB, as you can see in the circuit, that it is having a resistance and inductance connected in series with each other. So it is having an unknown inductance L1, having resistance R1. Now this arm AB is the impedance Z1. Impedance Z1 is connected in it. So Z1 impedance will be the equivalent impedance of this L1 and R1. As they are connected in series with each other, so Z1 will be equals to R1 plus the J omega L1. Okay, series combination of a resistance and a inductance. Next arm is arm BC. In arm BC, we are having only the resistance R3, which is a known non-inductive resistance. Here, this will be the impedance Z3. So Z3 will be equals to only this resistance R3. Then we are having the arm CD. In arm CD, we are having the series combination of a capacitor and a resistor. So arm CD is having a standard capacitor C4. So this standard capacitor C4 is connected in series with the known non-inductive resistance R4. So it will be a series combination of R4 and C4. So the impedance Z4 is the series combination of both these. Series combination of R4 plus XC. XC is the capacitive reactance. So the value of XC is what? 1 upon J omega C4. That is this. Putting its value here, this will be 1 upon J omega C4. Now this is 1 upon J omega, means 1 by J, it can be written as minus of J. So we can write it as R4 minus J upon omega C4. Okay. Then next we are having the arm DA. Arm DA was having the known non-inductive resistance R2. So this will be the impedance Z2 and Z2 will be equals to the resistance R2 only. So we have got the value of the four impedances Z1, Z2, Z3 and Z4. Z1 was R1 plus j omega L1, Z2 was R2, Z3 is R3 and Z4 is R4 minus of j upon omega C4. Now the balance equation was Z1, Z4 equals to Z2, Z3. This was the balance equation of an alternating current bridge. So we are going to put the value of these impedances in this balance equation and then we will get the value of Z1. Z1 is R1 plus j omega L1. Z4 is R4 minus of j upon omega C4. Z2 is R2 and Z3 is R3. Multiplying these, we will get R1, R4 minus of j R1 upon omega C4 plus j omega L1 R4 plus j and minus j. Here we are having j and j. When we multiply it, j square is equals to minus 1. We know that. So j and j square minus 1 and this minus it will become plus. So we will have plus sign and omega L1, omega and omega they will be cancelled. L1 upon this is C4. And this will be equals to R2, R3. Now in this equation you can see we are having the imaginary parts also and having real parts also. Imaginary parts are those terms which are having the j omega term in it and real parts are without the j omega term. So from this equation we will get two other equations. One is having only the real parts and other is having only the imaginary parts. So if we equate the real parts, R1 R4 plus L1 upon C4 is equals to R2 R3. This is one equation. Another equation is minus. When this minus will go to the right hand side of the this equal to sign, then it will become plus. So we will have j omega L1 R4 is equals to j upon omega C4 R1. Okay. So j and j it will be cancelled out. If we want to calculate the value of this R1, so R1 will be equals to omega and omega multiplied with each other. So omega square L1 R4 and this C4 is also multiplied with it. Okay. So we are getting the value of R1 from the imaginary part equation and this is the real part equation. Now if we put the value of this R1 in this equation, we can get L1. Okay. So let's find out the value of R1 and L1, both the unknown variables. R1 is omega square L1 R4 C4 multiplied with R4 plus L1 upon C4 equals to R2 R3. From this equation we want to find out L1. So take L1 as common. We are having here C4. So it will be omega square R4 square and C4 square plus here we are having 1 equals to R2 R3. So L1 will be equals to R2 R3 C4 upon 1 plus omega square R4 square C4 square. This is the value of the inductance L1 in terms of the known variables R2, R3, R4 and C4. Now R1 was omega square L1 R4 C4. Putting the value of L1 from here, we will get R1 as omega square C4 square R2 R3 and R4 upon 1 plus omega square C4 square and R4 square. We have just put the value of L1. So L1 is what? This R2 R3 C4, R2 R3 C4, and upon this term, because C4 is already present here, R4 is also present, so this will become C4 square R2 R3 R4 upon 1 plus omega square C4 square R4 square. So this is the value of R1. So you can see that we have calculated the value of the unknown variables L1 and R1, which are present in the unknown impedance Z1, R1 and J omega L1. Through this we can find out the unknown impedance. Okay. And here we have calculated the value of the self-inductance L1 of a coil which is having the resistance R1 in terms of the capacitor C4. Okay. Now, if we want to find out the quality factor of the coil, quality factor, it is a type of figure of merit, means it gives us the indication about the goodness or the performance of a coil, because quality factor is defined as the ratio of the power stored in the coil divided by the power dissipated by the coil. So, if we want to find out the quality factor, which is Q, it is equal to omega L1 upon R1. Okay, in a resonance circuit can be a series resonance circuit and parallel resonance circuit. So in the circuit which is where we are having a resistance also, inductance also and capacitance, the quality factor, it can be found out by the ratio of the inductive reactance divided by the resistance. So inductive reactance is what? XL is equals to omega L1. So omega L1 upon R1. L1 and R1 we have already calculated their values. We already know their value. So just putting its value in this equation, we can find out the quality factor. So Q will come out to be 1 upon omega C4 R4. Okay. So here you can see that this quality factor, it is in terms of the resistance and the capacitance only. Okay. So through this Hayes bridge, we have measured the self-inductance, we have measured this resistance R1, and also we have measured the quality factor. Now coming to the phasor diagram of the Hayes bridge. So in the phasor diagram, we draw the relationship between the various phasors of the current and the voltages present in the network. So phasor diagram, it will show us the relationship between the current and the voltage. Now here we are having three types of elements: resistance, capacitance and an inductor. So across the resistance, we know that the voltage and the current, they are in same phase with each other in the case of resistance. In the case of an inductor, the voltage, it leads the current by 90 degree. And in the case of a capacitor, the voltage lags the current by 90 degree. Here it leads and in the capacitor it lags. So we are going to use this relationship between voltage and the current to draw the phasor diagram for the bridge. Now again coming to the circuit diagram. In the circuit diagram, you can see that we are having the currents in the respective arm as I1, I2, I3 and I4. Now we have to take one phasor as a reference phasor. So we will take this current I1 as our reference phasor, and all the other vectors, they will be drawn with respect to this. So first we will draw the I1 phasor. Now I1 is the current flowing in this arm. So if we talk about the voltage drop across this resistance R1, then voltage drop will be I1 R1 and current is I1. So this voltage and current, they will be in same phase with each other. So I1 phasor we have already drawn. So I1 R1 will be in same phase with each this. So it will be drawn on the same line. Okay. Then we are having the voltage drop across this inductor. Across this inductor, voltage drop is I1 omega L1. Okay. And current is I1. So both this voltage and current, they will be 90-degree difference with each other. Inductor voltage is going to lead the current by 90-degree. Current is I1, voltage is going to lead it by 90-degree. So voltage will be drawn here. This is I1 omega L1. Now the total voltage drop across this AB arm is E1. E1 will be equal to the sum of the voltage drops. Okay, so it will be I1 R1 plus I1 omega L1. So if we draw the resultant here, it will be equals to E1. Okay. Now when this bridge is balanced, the detector is going to give us a null deflection. Null deflection means that the points B and D, they are at the same potential. Okay, same potential means that voltage drop E1 will be equal to E2. Okay, and the voltage drop E3 will be equals to E4. Now this detector is giving us null deflection, means no current is flowing in this arm. Okay, and the I1 will be equal to I3. Also this I2 will be equals to I4, because no current is flowing in this arm, so it will act as an open circuit. So I1 will be equals to I3 and I2 will be equals to I4. So we are going to use these relationships in our phasor diagram also. We have drawn the phasor for E1. Okay, so E1 phasor will be equal to E2. So E1 will be equals to E2. Now E2 is what? The potential drop across this resistance, that is I2 R2. So E1 is equals to E2, E2 is equals to I2 R2. Now this potential drop and the current I2 across the resistance, they will be in same phase. Okay, so the current I2, it will be drawn on the same line. And we have written here that this current I2 is equals to I4. So this phasor is also for the current I4, and I1 current is equal to the I3 current. Now coming to the BC arm. Here we are having the resistance R3. So potential drop will be I3 R3 and current is I3. Now these two will be in same phase with each other because it is across a resistance. So I3 we have already drawn. I3 R3 will be on the same line. So just draw this I3 R3, or we can say this is E3. Now E3 is equals to E4. Okay, we have already written here E3 is equals to E4. E4 is what? Potential drop across this CD arm. Now potential, when it is in the case of a series combination, potential will be divided. Okay, so this E4, it is equal to the sum of the potential across this C4 and the R4. Across C4 we are having the current I4. Current will be same in the series combination. So E4 is equal to voltage drop across this capacitor, that is I4 upon omega C4 plus I4 R4. It will be the sum of these two voltages. Now current across this capacitor is I4. across capacitor we are having the current I4 and potential drop is I4 upon omega C4. So this current and the potential, they will be in a phase relationship. The voltage, it is going to lag the current by 90 degree. I4 we have drawn on this line. Okay, so voltage will be 90 degree lagging behind it. So voltage will be draw a 90 degree angle, and here we will have the voltage drop, that is IC, we can say I4 upon omega C4. Voltage drop across capacitor and I4 was the current across the capacitor. We are having a 90 degree relationship between them. This was also 90 degree relationship. Okay. Now talking about this resistance, in case of resistance, the voltage and current, they are in same phase with each other. So I4, R4 and I4, they will be in same phase. I4 is drawn on this line. So here we will have the current voltage drop I4, R4 across the resistance. Now both these I4 upon omega C4 and I4 R4, their sum is equal to E4. E4 is drawn here. So when we draw the resultant of this I4 R4 and this I4 omega C4, it is equal to this E3 or E4. Okay. Now this was E1 or E2 and this was E3 and E4. So if we draw their resultant, it will be equal to the total EMF E, because E can be written as E1 plus E3, also it can be written as E2 plus E4. You can see here the total EMF is the sum of E1 plus E3 or E2 plus E4. So in this phasor diagram, we have drawn the relationship between all the voltages and the current across the circuit elements, the resistor, the inductor and the capacitor. We have considered the individual voltage drop across each of these elements and the current also across them. And then we have drawn the relationship between the current and the voltages in this phasor diagram. So this phasor diagram comprises the phasors of all the currents and voltages flowing in the circuit. Now coming to the advantages and disadvantages of the Hayes bridge. So the advantages and disadvantages of Hayes bridge are: advantage is that if you see the expression for the quality factor, it was 1 upon omega C4 R4. So this bridge gives us a very simple expression for calculating the quality factor. If we know C4 and R4, we can easily put their values here and can calculate the quality factor. Now this bridge is used to measure the quality factor of the coil, which is greater than 10. So the coils which are having high quality factor, their self-inductance can be measured through this Hayes bridge. Okay. And also it gives us a very simple expression for calculating the quality factor. Now coming to the disadvantages. The disadvantage is also it's what we have studied in the advantage, that it is used for the measurement of the self-inductance of coil which is greater than 10. So that becomes its disadvantage also, that it can be used only for the high Q coils. That is coils having high quality factor, that for that only we can use this Hayes bridge. For low Q values we cannot use this bridge. Okay. So these are the advantages and the disadvantages of the Hayes bridge. You can see here that if we are using a quality factor, if you want that quality factor is very high, then this resistance, it has to be very low. So here the value of the resistance R4 is very low, but in the case of Maxwell inductance capacitance bridge, the value of the resistance was very high, because there we were having the parallel combination between the capacitor and the resistance. So value of the resistance has to be very high if we want the quality factor to be high. Okay, but in this here we are having the resistance as very low, then only the quality factor has to will be high. So here the value of resistance is low, whereas in Maxwell the value of the resistance is very high. So these are the advantages and disadvantages of the Hayes bridge. So in this video we studied about the Hayes bridge, which is used for the measurement of self-inductance by comparing it with the value of a capacitor, and the capacitor and resistance, they are connected in series with each other. So I hope that this topic is clear to you. Thank you.